Alright, question 10. We've got this network. I've just redrawn it. I've also added letters on the end of my vertices, just so we know which vertice I'm talking about, and it makes it easy to follow along. So question 10 says, a family is going on holiday to France for the Olympics. A map of the cities they wish to travel to are shown below, with the vertices representing the towns and the edges, vertices representing the location of Olympic events, venues, and the edges representing the roads connecting the locations together. Pretty simple stuff. That. Part A is determine the Hamiltonian cycle that the family can follow. State why it is an Hamiltonian cycle. Alright, so exercise 10.4 in our textbook, it says, if a graph has a path that includes every vertex exactly once, while ending at the initial vertex, this is a Hamiltonian graph. This pathway is called an Hamiltonian cycle. So you should be able to go from one vertex to the other at least exactly once and still start at the vertex you started with. So here they've started at A, gone to B, gone to C, gone down to E, across to D, and they've looped back at A where they started. We need to make sure we can do this same process with the graph we have. So let's say I start at A, I want to go to all other vertices and come back to A. Obviously the easiest one is to follow the outside. There are multiple solutions to these problems for some cases, so if you get a different answer to what I have on this video, that is fine. But just to follow the logic of keep it simple stupid, we're going to go along the outside. So you go from A to C, C to D, D to E, E to F, F to B, and then back to I, starting point A. You don't have to do this, but I'm just drawing in the arrows so we know which way we went and where our start is. Alright, so determine the Hamiltonian cycle, that's in orange. State why it is a Hamiltonian cycle, that will be because it is a Hamiltonian cycle because all vertices were traveled to, I guess, exactly once, and we ended at the same vertex which we started at. A statement like that is all you need to get the marks for this question. And then part B, list any vertex that the family does not travel on. Well, the highlighted is what they travel on, so anything not highlighted is what they didn't travel on. Just realized I didn't call that G. Alright, so they didn't travel from A, G, They didn't go from BG. They didn't go to GC, GF, and GE. That's it. We've listed them down. And EC, sorry. Alright, double checking. Got that. And EC, cool. We've got all our edges. And then part C is determine the ULA trail that the family can follow to visit each event. Justify these decisions using mathematical reasoning. That brings us to our next thing. What the hell is an ULA trail? An Eulerian trail according to the textbook. An Eulerian trail is a trail by which you can travel around an Eulerian graph. Well, that explains right. An Eulerian graph is a connected graph which allows you to start at a vertex, traverse each edge only once, and return to the vertex from which you started. So that means... Alright guys, I had to pause the video because I had to have another look at this because it didn't really make sense. But then I read the textbook again and it said a graph is Eulerian if each vertex has an even degree. So if every vertex has an even number of degrees, a graph is Eulerian. So all vertices must have an even degree, or there must be exactly two vertices of odd edges. So two vertices can be odd, otherwise all of them have to be even. Okay, so let's just start here then. I'm just going to find the degree of each vertex then. So the degree of A, we've got 1, 2, 3. Degree of B, we've got 1, 2, 3. Degree of C, we've got 1, 2, 3, 4. Degree of D, 1, 2. Degree of E, 1, 2, 3, 4. Degree of F, 1, 2, 3. And degree of G is 1, 2, 3, 4, 5. So again, that's what we have. So if we read this again, for an Eulerian trail to exist, all vertices must have an even degree. Well, we've got odd numbers, so that's not right. Or there must be exactly two vertices of odd degrees. We've got 4 vertices with an odd number of degrees. So if I highlight them there, there's our 4 vertices with an odd number of degrees. So that means for this network there is no Eulerian trail. So for this network, an Eulerian trail does not exist. and working at our degrees is using our mathematical reasoning. So that's how we solve that question.